Okay, so we may just now, I just rewrite here the Hamiltonian, so we have that at disposal. So we have the summation over R of the square of the momentum. Then we have the R different from 0. And then there is the dynamic term. Okay. Before going on with the calculation, I just recall some of the properties of this matrix, since I will need to use those properties later. So D is, so concerning the indexes of the matrix, D alpha beta is equal to D beta alpha. So D is a symmetric matrix, and this is due to the fact that the matrix is defined in terms of the second derivative of the potential with respect to the coordinates. So within D, we have the, let's say, second derivative of phi with respect to, I just write, this is just to say derivative with respect to coordinate, the coordinate of the vector that is alpha, and derivative with respect to the coordinate of the vector that is beta. So this is just to say I would write dx dz or dx dy. So this is just to represent each of the coordinates. And since this matrix is symmetric, then also the D matrix that is defined in terms of this, of the second derivative of phi, is symmetric itself. Then D so we have the symmetry, then we have that if we change the sign of the variable that is let's say of the vector that is included in the definition of the matrix, then the matrix is always the same. And this property is due to the inversion symmetry of the Bravais lattice. So in this case, let's say if you choose vector r, for instance, then you know that vector minus r is again a vector of the lattice, and then you expect that since D is defined in terms of the interaction potential, the inversion symmetry tells you that if coordinate r is in the lattice, then also coordinate minus r is in the lattice. And then you expect that the interaction depends on the distance. So on the relative position, not on the absolute position. So in this way, if you know that vector r and minus r belong to the lattice, then the relative position is always the same between the 2 points. So in this case, this equality again comes from the mainly from the inversion symmetry and also from the structure of the potential. And then if U of r is equal to D, that means if you take all the ions in the system and you apply exactly the same displacement to all the ions, then this has to be equal to 0. Because why that should be 0. Because if you take the static configuration and you just translate all the ions with the same displacement, you are just taking the solid and translating the full solid by an amount that is equal to D. So at this point, you have no change. Let's say the energy of the lattice is always the same because you do not displace, you do not change the relative position of the ions. The relative positions are always the same. You just make a translation of the full solid. So in this case, you expect that a uniform translation of the solid should not change the dynamic term because you have the static term for that. So the static term means all the ions in the equilibrium position, and if starting from that you displace all the ions by the same amount, then you have again only the let's say the static term, not the dynamic one, because you have no relative change of the position of the ions. So due to that, this summation is expected to be 0, or more in general, because D is a constant and D is again a constant, also the summation over R and R prime of D of R minus R prime is expected to be 0. So in general, again, if you make a translation of a constant using a constant vector, then this summation should be equal to 0 because you have no dynamic contribution to the energy. Okay, so at this point, since we have made an assumption concerning the structure of the displacement field, we should find a constraint concerning K and omega. So it's just like as if you should find a sort of dispersion relationship between omega and K. For instance, for electromagnetic waves, you have that omega and K are proportional with each other. But now we should find a new dispersion relationship between omega and K, considering the fact that omega and K describe the oscillation of the ions, the displacement field, a possible displacement field concerning the oscillation of the ions when those ions are interacting within the solid. And at this point, we may write down the equivalent of the second law of dynamics for the coordinate U. So in this case, we have the P is the, let's say, the derivative of U is P, and to write down the equation of motion of U, we need a constraint concerning the second derivative of U. So the second derivative of U is P prime. We know that P prime, since we are using the Hamilton formalism, if we know the Hamiltonian, the derivative of P is minus the derivative of the Hamiltonian with respect to U. So U and P are conjugated variables. So P prime is equal to minus the derivative of the Hamiltonian with respect to U. So, and P prime is, P is the momentum, so mass time velocity. So the second derivative of the first derivative of that is mass times U, second derivative of, here I wrote, so this is correct. So in this case, we have that the second derivative of U of R times the mass of the ion is equal to minus the derivative of the Hamiltonian with respect to U of R. So let's just write down this equation. Just one comment, as I will apply that later. Here we have 1/2. Then we have the summation over R and R prime of U of R, the D matrix, and U of R prime. Now I have to perform the derivative with respect to, U just U of R, not R prime. And if you notice here, I have U of R on one side, in this case on the left side of the matrix, but if I fix the value of R, then at some point also R prime will have, also R prime will be equal to R. So I have the opportunity to find a specific coordinate both on the left side of this matrix and on the right side of the matrix. So I expect to have two contributions to this derivative, one coming from the left part of this matrix and one coming from the right part of the matrix. So this 1/2 will disappear because I have two contributions, two terms that contribute to this derivative, and due to the fact that this matrix is a symmetric matrix, multiplying on this side or on the other side is the same. Oops. So I will write this as the m times the second derivative of u of r is equal to, again, minus the derivative of the Hamiltonian with respect to u of r, that is equal to the summation over r and r prime d of r minus r prime u of r prime. So and with a minus sign in front. At this point, I may introduce into this expression the equation of motion, the trial equation for u, the displacement. Again, u and e are vectors. From now on, I will not use always the vector sign, but please keep in mind that u and e are always vectors. So in this case, I have m times the amplitude times the vector. Then I have the phase. Then I have a second derivative of that with respect to time. So I have minus omega square due to the second derivative. And this is equal to minus summation over r and r prime of d of r minus r prime. Then I have the amplitude and the polarization vector. Here I have the amplitude on both sides. It's always the same, so I may simplify the amplitude. And I may also simplify the time dependence, because I have a phase with minus omega t on this side and the phase with minus omega t on the other side. I may not simplify the position dependence because here I have r and on the other side I have r prime. So in this case I have that m minus m omega squared, the polarization vector, is equal to minus summation over r and r prime of d r minus r prime. Then I have e to the I k r prime that is due to this phase on the right, and then I have minus r that is due to the phase that was on the left. So here I have minus r. So in this case, if you sorry for that. Here I have not the double summation because I made the derivative with respect to r, so I have to drop the summation over r. So this is not correct. I just have the summation over r prime because I was making the derivative with respect to u of r, so no summation over r. Okay, so if I define r minus r prime to be r second, then I have that this is equal to minus the summation over r second. Sorry, and here we have the polarization vector E. So we have the summation over r second of d of r second e to the minus I k r second vector E. At this point, we may simplify the minus sign that we have in front of all the terms here. So the final equation is m omega square E is equal to this, that is just a matrix. So I have the matrix D times a phase, and then a summation of all those matrices that have exactly the same structure. So this summation gives rise to a new matrix that is called dk, because this matrix, after you have performed the summation over r second, depends just on the wave vector k times the polarization vector E. So dk is called dynamical matrix. And just consider the definition of that. D of k is symmetric because all the matrices that are, let's say, all the D of R matrices are symmetric. So you're summing up symmetrical matrix, so you end up with a symmetrical matrix. Then what happens? And K is a vector belonging to the reciprocal space. What happens if you make a translation of that? If you write K plus G, where G is a vector of the reciprocal lattice, that is equal to a summation over R of D of R e to the I k minus I k times R, then e to the minus I g times R. But for the definition of vector belonging to the reciprocal lattice, this is 1. So this is equal to D of k. And this is an important point because here we are solving a problem where we have a matrix. This is at the end an eigenvalue problem because you are just writing down that dk applied to the vector E has to be equal to a coefficient times E. So this is just an eigenvalue problem. And you are saying that the matrix that you have for that eigenvalue problem is a matrix that is periodical in the reciprocal space and that has the same periodicity of the reciprocal lattice. So this means that also the solutions of that problem, we have exactly the same symmetry. So all the solutions that we will find after the application of this matrix will be solutions that will be periodical in the reciprocal space, and those solutions will have the same periodicity of the reciprocal lattice. So this is important. The dynamical matrix is periodical in the reciprocal space. And the final point is that this is exactly the same symmetry that was observed for the energy of the electrons. And due to that symmetry, we had the opportunity to discuss the problem all just in the first Brillouin zone. As the dynamical matrix has exactly the same symmetry, then we end up with the same conclusion. That means all the problems concerning the oscillations of the ions in the lattice can be discussed just using the wave vectors belonging to the first Brillouin zone. So from this point of view, the, let's say, dynamics of the electrons and the dynamics of the lattice oscillations are defined exactly in the same volume of the reciprocal space. So electrons and lattice oscillations share the same volume. So the two problems can be solved exactly in the same volume in the reciprocal space, thanks to the periodicity that both problems have in the reciprocal space. Since now going back to this eigenvalue problem, we know that D of K is a symmetrical matrix. If that matrix was also real, then we could apply the spectral problem to be sure that there's always a solution. Sorry, if we could apply the spectral theorem, we may conclude that dk has always three solutions that are three orthogonal vectors in the in space. So at the moment, we don't know if D of K is real or complex, because going back to the definition, we have a phase. So in principle, D of K may be a complex matrix. So what one tries to do is to consider whether D of K is a real matrix or not. To discuss that, let's just write the definition of D. So D of K is a summation over R of D of R e to the minus I K R. So this is the general definition. At this point, I may just rewrite that as 1/2 summation over R of D of R e to the minus I K R plus so here I just wrote twice the same thing. If we now consider the second term, the D of R matrix has this property. So D of R is equal to D of minus R. So this means that if I change the index of summation from R to minus R, what happens is the following. Here I have D of R e to the minus I K R. Then I have sum over R of D of R e to the I K R. Because if I change the sign, I have to change the sign both in the phase and in the matrix, but D of R is equal to D of minus R. So I may suppress the sign variation within the matrix. So at the end, I have just D of R here, and the only change of sign is within the phase. Due to that, I may sum up. I may join these two sums just like 1/2 summation over R of D of R that multiplies e to the minus I K R plus e to the I K R. And you may recognize here something that resembles the definition of a cosine, because if I take this factor 2 within the parentheses, I have a cosine of KR. So this is equal to summation over R of D of R cosine of KR. If you remember before, we saw that if you sum this matrix with multiplied by a constant term, then the full summation is equal to 0. So this means that here I may include the constant term without any problem, because if here I introduce a constant coefficient, then the presence of that coefficient doesn't change the final sum, because the final sum with that coefficient will be equal to 0. And in this case, I sum -1. And In this case, you may also apply the I don't remember exactly there should be a duplication formula. So the cosine of kr is equal to the cosine square of kr divided by 2 minus the sine square of kr divided by 2. So this is just the general property of the trigonometric functions. So you may just introduce this expression into this formula, and then if you write the square of the cosine as 1 minus the square of the sine, you have 1 minus twice sine square of kr divided by 2. And considering the fact that you have also a minus sign here, sorry, a minus 1 here, then this plus 1 here and this minus 1 here disappear. So the final point is that this is equal to summation over r d of r that multiplies minus 2 sine square of kr divided by 2. And this is for sure real. So we have that the d of k, the dynamical matrix, is real and symmetric. So we may apply the spectral theorem, and we may say that this eigenvalue problem has for sure a solution. So for each value of k belonging to the reciprocal space, in particular belonging to the first Brillouin zone, we may find 3 solutions. So we may we have the opportunity to let the matrix. So if we change the coordinates, we may have the opportunity to have that the dynamical matrix is diagonal with 3 coefficients different from 0 over the diagonal. So to express the fact that for each value of k, we have 3 possible solutions, this means that the frequency omega square will depend both on k and on another index that is generally called S. In a while, I will comment about that. If we have, and here we have the solution, the eigenvector, and in this case, also the eigenvector will depend on k and on S, the second index. If we have the opportunity to write the matrix in a diagonal form using the basis that is given by the 3 eigenvectors, then this is the application of D to the vector will give rise to the eigenvalue that is in general called lambda, that will depend both on k and on S, and EA KS. So at this point, we have that m omega square ks is equal to lambda ks. So we have a connection between the frequency, that is omega square, and the wave vector, as the dynamical matrix depends on the wave vector. So the wave vector dependence comes from lambda, and so lambda again depends on the wave vector, So we have a relationship between the omega, the frequency, and k. So we have omega squared ks is equal to lambda ks divided by m. Just a comment concerning the dependence. Let's just consider this matrix. So d of k is equal to minus 2 summation over r of d of r sine square of k r divided by 2 if this scalar product, so if k times r is small, we may perform an expansion of the sine square or of the sine with respect to the with respect to 0. So this is minus 2 summation over r of d of r. In this case, we have k times r squared divided by 4, and we may simplify this, so we have a 2-factor here. We may rewrite what we have within the parentheses as k versor times r squared and k modulus squared. So I just leave the, let's say, vector k within the parentheses for the scalar product, and I take the modulus of k and I take that modulus out of the parentheses. In this approximation, so if k times r is close to 0, what we have is that m omega square of ks e of ks is equal to d of k e ks. This is proportional to k squared modulus times minus 1/2 summation over r of d of r k versor times r squared EKS. So I have just written the expression of D using this approximation. So you have that irrespective of this coefficient, sorry, that is not the coefficient, it is that is proportional to the dynamical matrix. So, and the important point is that this term here does not depend on the K modulus. The only dependence on K modulus is here out of the parentheses. So we have here a K squared and here omega squared. So we have that for small values of this scalar product. So if K times R is small, then omega Ks is proportional to K modulus. So what we expect is that for when K is close to 0, the omega versus K dependence is linear. So if we make a plot, so if we plot omega as a function of K in the first below n zone, close to 0, if we are close to, for values of k close to 0, the dependence is linear. Another important point is that that on the right side, the dependence is on k squared. If the dependence is on k squared, that means that the omega versus wave vector dependence is even. So the omega versus k dependence is even. And this can be also observed here if you notice the this sign square. So if you fix everything and you just substitute k with minus k, here you have a sine squared, so the final result is the same. So the dependence is an even dependence. So due to that, what we expect is that the dependence is linear here, but we have to recall that we have the parameter s. So for each value of k, I have a number of solutions that is equal to 3. So I expect that I have 3 possible eigenvalues for each value of k. So I have 3 different values of the frequency for each value of k. So due to that, I have 3 linear dependencies here. So 3 solutions due to the fact that I have the index S, and the index S allows me to access the 3 solutions that I have for each value of k. So the matrix is a 3 per 3 matrix. So I have 3 possible solutions for each value of the wave vector. What it can be seen is that if you, let's say, if you go on with this dependence to see what happens when you reach the border of the zone, you have this behavior. So as you approach the zone, the dependence is no more linear, and you have that you approach the border of the zone with a derivative that is equal to 0, as that happened for the electrons. So you have that close to the border of the zone, the derivative of that is equal to 0. And now an important comment concerning this approximation. So this approximation is important because why should k scalar product R be small? Because in principle, you may say, okay, if the wave vector is close to the origin, then the first term here is small. But in principle, R is a vector of the Bravais lattice. So R, in principle, may have, let's say, may connect one ion on one side of the solid with another ion on the opposite side of the solid. So in principle, R has no upper boundary. So K scalar product R is not said, may not be small even for small values of K. So why should you consider this to be close to 0? An important point here is to recall that the R is the vector that connects the 2 ions that are interacting. So we started up with an expression of the potential that was phi of R minus R prime. When we changed the variables, that was changed into phi of R. So R is the vector that joins the two ions that are interacting with each other. As we saw when we considered the contribution of the electrons to the dielectric constant, the rearrangement of the electrons in the system is able to screen the effect of the interaction potential over a short distance. So in principle, even if the ion on the right side of the solid could interact with the ion that you have on the opposite side of the solid, that is not expected due to the fact that you have a screening contribution from the electrons, and as we will see later, also from the ions. So both the electrons, as we have seen, and the ions, as we will see later, contribute to the screening of the actual interaction potential. So this means that R, even if R has no upper boundary, because there are no limitations concerning R, then there is an upper boundary that is due to the fact that the potential, the interaction potential, has not an infinite range, but has a range of interaction that is limited by the screening contribution. So due to that, there is also an upper boundary over R. So we have an upper boundary over K because K is limited in the first Brillouin zone, and also an upper boundary over R that is due to the interaction range of the potential. So due to that, it's possible to say that this scalar product is close to zero. Otherwise, that would not be possible. Now, in your opinion, what is the physical motivation behind the fact that here the omega versus wave vector dependence is, let's say, linear? But my point is, why, in your opinion, omega goes to zero as K goes to zero? So why the frequency of an oscillation that has a very, very large wavelength is close to zero, or is very small?
Maybe because it is too fast to be felt by the ions.
Could you please explain what you mean with too fast?
I don't know.
Or also in Italian, if you prefer.
Non so, lei ha detto che ha un vettore d'onda molto lungo, giusto?
Diciamo un K piccolo e quindi una lunghezza d'onda molto elevata.
Una lunghezza d'onda molto elevata. No, scusi, stavo pensando un'altra cosa. Volevo dire che la scala non era compatibile. Nel senso, la scala dell'oscillazione era troppo grande per essere sentita dagli ioni.
Ok, yeah, that is the correct say.
Avevo pensato un'altra cosa, cioè mi sono confusa poi dicendolo.
Okay, no problem, but that is the, let's say, the correct idea. So let's say, if we consider if we suppose to have the ions in the system, and I just make a chain here, a line here, just to make a simple design, simple picture. If K is small, then the wavelength of the oscillation is very, very large. So if we want to plot the amplitude of oscillation, then the amplitude of oscillation has a small variation over space. So here, if we plot the amplitude as a function of the position, we have a huge wavelength, so the amplitude changes slightly. So this means that the deviation from equilibrium that corresponds to this ion, and the deviation from equilibrium that corresponds to this ion are quite similar. So if you remember the spring mass problem, so if you have two masses that are connected by a spring, and you call K the, K is similar to the wave vector, but this is capital K, it is the elastic constant of the spring, then what we have is that the frequency of oscillation depends on the square root of the elastic constant divided by the mass to the power of 1/2. So what does the fact that the amplitude of oscillation is similar here means? Is that if you consider the two masses, if the displacement of those two masses is exactly the same, this means that the spring that connects those two masses is not extended nor compressed. Or in other words, it's just like if that spring is not, you have nearly no perturbation on that spring. Or in other words, it's just like as if the spring is is not stiff, because the relative displacement of the two masses is nearly zero. So the spring is not subjected to an external force that compresses the spring or extends the spring, but those two masses are nearly in the relative equilibrium position. So in this situation, it's just like as if the elastic constant of the spring was very small. So you have that the frequency goes to zero. Differently, if you have that the amplitude of oscillation, if K increases, then the amplitude of oscillation changes more rapidly from ion to ion. So you have that the elastic constant, let's say, the spring, that connects different masses is more, is subjected to an extension or to a compression. So due to that, you see that you have that this K is not close to zero, but is different from zero. So that at that point, you have a frequency value that is not negligible in that configuration. And please also note that, as you see in this picture, if this ion has a displacement, an ion that is close to that has a similar displacement, where similar means in a direction that is similar to the first one. So in this case, we have that the displacement is an in-phase displacement. So if the first ion moves, let's say, just for instance, to the right, then also the second ion moves to the right, just with a different amplitude. So these are in-phase oscillation. So in this situation, we have that these three branches are three different branches that correspond to in-phase oscillations of the ions. And what is the meaning of the three possible solutions? The meaning of the three possible solutions is the following. We have the vector K the vector K is the direction of propagation of the wave. So we have a wave that goes through the solid. So we have a displacement of the ions that is described by this so we have this plane wave that propagates through the solid, and the amplitude, this wave propagates so that each ion has its own oscillation with respect to the equilibrium position. So this is what we called at the beginning U of R. And to K and S, we have that EK and S. So S is 1, 2, and 3. So we have 3 possible wave vectors, eigenvectors corresponding to the eigenvalue problem that was connected to the dynamical matrix. We may choose, so in general, it's possible to choose one of the 3 vectors parallel to K and the other 2 vectors orthogonal to K. So we have that the three vectors are one parallel to K. The other 2 vectors are perpendicular to K. The vector that is parallel to K make a sort of longitudinal oscillation, because you in longitudinal waves you have that the oscillation is in the same direction of the propagation, in the same direction of that of propagation of the wave. Then you have also 2 transfer waves that are whose direction of oscillation is orthogonal to the direction of propagation. And as you have in phase oscillations, and one of the oscillations is a longitudinal one, what does that recall in your mind? What is a typical wave that is longitudinal and in phase and produces in phase oscillations of the elements that participate to this oscillation itself? That is an acoustic wave. So in acoustic waves, you have longitudinal oscillations and in phase oscillations. So due to this similarity, you have that these 3 branches, so the 3 branches that you have so you have 1, 2, and 3, so the 3 different branches. And those 3 branches are called acoustic branches. And in particular, if you notice here, so in general, we know that omega Ks depends both on K and on the index S. If you remember what we did with electrons, we said the dependence, the K parameter is a discrete parameter, but due to the fact that the distance between one K point and the next is very, very small with respect to the size of the Brillouin zone, we may consider this dependence to be nearly a continuous dependence. So that is often written as omega of K with index S. So that is to say, that is just a consequence of the fact that the K values are very, very dense in this range of wave vectors. If you see what happens here for small values of the wave vector, we have that if K is close to 0, omega S of K can be written as K times a coefficient, because we have a linear dependence. And this coefficient may depend on the index S and may also depend on the direction of K. So in general, let's say the dependence on the modulus is out here, and here we have the dependence on the direction, just on the orientation, and on the index of the index S. This can be written also as K. If you let's say, if you consider k not to be equal to 0, but to be, let's say, small, quite close to 0, the value of omega for a k value that is very close to 0 can be written as k times the derivative of k of omega with respect to k. So what is the meaning of this coefficient? If you remember the dispersion relationship that is found for electromagnetic waves, this coefficient here is the speed of the perturbation, if the speed of the wave. So for electromagnetic waves, this is the speed of light. So this is to say that c in this representation is the speed of this perturbation of this wave that propagates through the solid, that in this case is the speed is proportional to k because we are in the linear regime, and as that resembles an acoustic wave, that is exactly the speed of the, let's say, of the sound within the solid. So c in this case for small values of k is actually the speed of the sound that propagates through the solid, and that speed can be evaluated by making the derivative of omega with respect to k. And if you remember, this expression is the expression that represents when you have not a single wave, but you have a combination of waves that moves through a medium. The derivative of omega with respect to the wave vector is the group velocity. So that derivative there is the group and now, if you allow me to do that, just I open a parenthesis. Omega in general, what is the connection in general between a frequency and the energy? In general, you write that the energy is h bar times the frequency. So in general, one writes energy equal to h bar frequency. So if we just use that, we have that derivative with respect to k of omega is equal to is equal to 1 divided by h bar, the derivative with respect to k of the energy. And if you remember, this is exactly the definition of speed for one electron. So looking back to the electron problem, we may say that the velocity that was found in the case of Bloch electron is a sort of group velocity of the wave packet that describes the electron, because we said we may not describe the electron with a single wave function. We have to build up a sort of combination of wave functions with the weight that depends on the wave vector, and that combination builds up the actual wave that describes the propagation of the electron through the solid. So the definition of velocity for the electrons was a sort of group velocity for that wave packet that propagates through the solid. So okay, just I close the parenthesis. So now if we go back here, we have that that for small values of k, this derivative is just a coefficient. So that coefficient represents the speed of sound within the solid. So at that point, let's say just in a rough way, you may measure the speed of sound within the solid. The speed of sound depends on omega. Omega depends on d. D depends on the potential. So you may have an indication concerning the potential just accessing, for instance, the value of the velocity of the sound within the solid. So if you just want a rough indication concerning the strength of the interaction potential, you may just have an idea about that by measuring the speed of sound within the solid, because the speed of sound is due to the propagation of an elastic wave within the solid. and the equation ruling the propagation of that wave is an equation where we also have the contribution of the interaction potential between the ions. So just to summarize, it's about 11:30. What we have seen up to now is that the general oscillation of one ion within the oscillation of all the ions within the solid can be written as a combination of waves, like this one here. Each wave is characterized by a specific value of k that is within the first Brillouin zone, and by a corresponding value for the frequency omega. So we have a sort of combination of normal modes of oscillation. So in this case, what we have found is that the solid is able to express different normal modes of oscillation. How many of them are found? We know that within the first Brillouin zone, we have a number of wave vectors that is equal to n, where n is the number of ions. So the total number of normal modes of oscillation is equal to n, because n are the number of k values that we have within the first Brillouin zone, times 3, because we have 3 branches. So the final result of this calculus is that any arbitrary oscillation of the system can be expressed as a combination of normal modes of oscillation, and the normal modes of oscillation are found in a number that is equal to 3 times the number of ions that you have in the system. Okay, and the dispersion relationship between the frequency and the wave vector is linear in the initial part of this dependence, and then that dependence switches from linear to nearly constant when we reach the border of the zone, because here we have that the derivative of omega with respect to k is close to 0. So in this picture, again, we have a total number of 3n normal modes of oscillation. Tomorrow, I will go on with the analysis of this result and see what is the consequence of that concerning the evaluation of the specific heat. Okay, do you have comments or questions? Also for those who are connected.
No question, of course.
Okay, so in this case, I stop the registration